All right, it looks like we're recording. Let me know if there are any technical problems. Otherwise, welcome to day number 2 of C and Software Tools class. We got a lot of little things that we're supposed to do today. And kind of like our first day of class, the intent is as quickly as we can, we're going to try to get you to where you can write some non-trivial programs in C, leveraging a lot of stuff that you already know from Java and from just knowing how to write code in general. This is our plan for today. We're going to learn how to do console I/O using a couple of different mechanisms. And then we're going to step back and look at some bigger ideas of how C compares to Java and sort of how a C program gets built and executed. And then at the end, we'll talk a little bit about our coding style guide. If you look at the top of our page in Moodle, it has a link to our coding style guide. One of your first week tasks should be to read over that so you don't lose points for little things like style, but we'll try to touch on some of the main points of the coding style guide there at the end of lecture today. As always, if you have a question, just unmute yourself and speak up and I'll try and take it right away. You're welcome to put stuff in the chat, but I usually don't get to check on that until the end of lecture. All right, let's go. In C, kind of like when you write a Java program, you've got access to this giant Java API that provides ways of doing network communication and containers and I/O and all kinds of things. C has a similar but much smaller library called the standard library. That's part of the C programming language, or I guess it's kind of an add-on to the C programming language that's commonly there when you're developing code, and it provides support for a lot of the same kinds of things, for doing I/O, for managing memory, for working with strings, things like that. One of the first parts of the standard library that we're going to use is the I/O part of the library called the standard I/O library. That's for, at least initially, it's going to be for reading and writing stuff from the terminal. And later we'll use that same part of the library to read and write from files. To use the library, you need to include the header for that library. And we've already seen this line, that pound include standard io.h inside angle brackets. That's how you tell the compiler that you're going to use stuff from the standard IO library. And then when it sees you making calls to things like printf, or later we'll see getchar, it'll know about those things already. So we will be using include standard io.h in almost every program we write. We'll also use standard lib.h. That's another header that we'll normally include, and it includes a lot of the central stuff in the C programming language that you would use in almost every program. So those two will be at the top of about everything that we write. Those kinds of statements in general, things that start with a pound sign, those are called preprocessor directives. We'll talk about that a moment or a little bit later in class today. And then we got a whole day that we spend talking about the preprocessor. Those are messages to this compilation step that happens really early in C compiling. A step that Java doesn't really have at all. So we'll spend a little bit of time talking about that. And then again, we'll return to it and spend more time later. We'll start by talking about I/O in C, input and output. And a C program, just like Java, starts up with kind of 3 places that it can do I/O for free. These places are called streams. That's just the C word for a thing that you can read stuff from or write stuff to. And just like a Java program, when a C program starts up, it's got 3 streams that are there already: standard input, standard output, and standard error. Standard input, by default, that corresponds to reading input that's typed in at the terminal, the same window where you ran the program. Standard output is where you print output to the terminal. And just like Java, standard error also by default goes to the terminal, but it's for error messages. And the reason you've got those 2 different streams that go to the same place is you can send them to different places if you want. You could send error messages to a different, maybe to a file if you wanted to save those, even though regular program output could keep going to the terminal. All of these streams, at least all the input streams, will let you read as long as there's more input available. Uh, when they run out of input, you'll get what's called the end of file condition on that stream. Even the terminal can exhibit the end of file condition, so you can be trying to read from it, and it can look like there's no more input to be read. The way you signal the end of file condition, I know for a terminal, until you close the terminal, the user could still keep typing stuff, but if you want to, you can signal the end of file condition. You can make a program think it's hit the end of input by typing, well, on a Unix machine, by typing Control-D. So that means if you're running a program on a Unix machine, even if you're logged in from a different machine, but if you're running it in a terminal window that's on a Unix machine, typing Control-D should signal the end of file condition. If your program's actually running on a Windows machine, if you built it on your Windows laptop and you're running it on that laptop, you're not logged in remotely to some Unix machine, then the same thing should be Control-Z, I think, on Windows. So if you want to make terminal input look like there's no more of it, that's a way to signal the end of file condition, even on a terminal. These streams can be redirected. Eventually, we'll learn how to open files for input and output. I think we learned that on about day 9 of class. Until we know how to do that, we'll read and write from files using I/O redirection. We can take a program that was made to read from the terminal, and we can trick it into reading from a file instead using the syntax I'm showing down at the bottom of this slide. So if you run, I'll point to it with my mouse here, if you run a program, and then you do a lesser than, and then any input file you want to read from, whenever this program tries to read from the terminal, it'll really be getting input from this file. So that's a way. Java's the same way. You probably did this same trick in Java, because it doesn't depend on the programming language. This is something that your shell does for you. It can run any program and trick it into reading from a file whenever it tries to read from a terminal. So if we write a program, if we run a program and we use this syntax, then whenever it tries to read from the terminal, it'll really be getting characters from whatever file we pick. Same with output. If we use a greater than sign instead, then whenever it tries to send output to the terminal, it'll really go to this file instead. This is kind of handy for being able to run a program and test it with particular test input. We use this all the time when we're testing our programs. And like I said, until we learn how to read and write files directly, until we learn how to write our own C code to do that, this will be our way of doing file I/O, just using the standard terminal I/O calls. Questions before we move on? So I just said the word terminal, or the term terminal I/O calls. How do you ask to read or write from the terminal? We're going to see 4 function calls that you can make in C. Remember, in C, what we would normally call a method in Java, we call that a function in C, a function because it could return a value, and it's not part of a class. All functions are just declared at file scope. They're not part of anything. So to learn how to do I/O, we've got to learn a few functions that'll let us get stuff from the terminal and put stuff on the terminal. And we'll learn 2 types of calls. One for doing character I/O, for reading or writing one character at a time. And then later we'll learn a couple of calls for doing formatted I/O, for reading numbers and strings from the terminal, bigger stuff from the terminal. So first, let's look at the character by character I/O. So if you include standard io.h, you get access to this function, getChar. I've listed it up there. getChar doesn't take any parameters. In C, the way you can show that a function doesn't take any parameters is you can just put the word void inside the parameter list, and that tells the compiler you don't have to pass anything to this function, or I guess better, you can't pass anything to this function. So when you call getChar, you can just give it empty parentheses, you don't pass anything to it, and it returns a numeric code for whatever next character it reads. That's this integer return value out at the front. The integer is just, again, it's the numeric code for whatever you read. Just like in Java, every character has a numeric code that that stands for that character. And if you want to know what the numeric code is for a character, well, there's a big table that shows you all those codes. We'll see that, I think it's 2 lectures from now. So there's a big table that tells you the numeric code for every standard character. But I almost never have to look at that table because when you put a character inside single quotes, that's what it means. It means what is the numeric code for this character. So if you put an A inside single quotes, and we got an example program in a moment that shows this off. If you put an A inside single quotes, you're asking for the numeric code for a character. So this function gets them, I probably didn't say this most important part, it gets the next character of input from the terminal. So whatever the next character was that was typed by the user. Usually it's only going to see input after the user has entered a whole line. So the user will type a bunch of characters, and then when they hit enter, the program can get all of those characters one after another in the order that they were typed by calling this function over and over again, once to get each character. So if it's successful, it returns whatever the numeric code for the next character is. If not, it returns a special constant EOF. The value of EOF is actually -1, so none of the legal characters have a value of -1. EOF uses that value -1 to signal that there's no more input. It's handy to know that EOF is -1, but you almost never need that in your program since we've already got a named constant for it. When you include standard io.h, you get access to this constant capital EOF. And if you want to write your code so that it's readable, it makes sense to use that name rather than -1 whenever you want to talk about EOF. So again, it has a value of -1, but in your programs, you would almost always want to use this named constant EOF for that. So when you call getChar, it returns the numeric code for whatever the next character is on the terminal, really the numeric code for whatever the next byte of input is. So you could use this to read input 1 byte at a time, where each byte, each 8-bit byte represents the code for a character at the terminal. Because it could return any legal byte value. When it returns EOF, it has to return a value that's different from every legal byte value. That's why this function returns type int rather than char. We've got a perfectly good char type in C, but this function returns int instead so that it has enough different values it can return to return the legal code for every character, plus 1 extra value to indicate, well, there wasn't any more input. So I guess EOF, the code for EOF, is different from every legal character that this function could return, and different from every possible byte value it could return. So this function returns int instead of char so that it's got enough different return values it can return back to have 1 extra value to say there wasn't any more input. There's some comments popping up, which is fine. Questions before I try to move on? So this function is for reading 1 character at a time from the terminal. It returns EOF when there's no more input to be read. It's usually a mistake to take the return value of this and put it in a character variable. I just tried to make a big deal about how it returns int. And the reason for that is if you take the return value of this and you put it in a char, then there are going to be some cases where you can't really tell whether you've hit the end of file or not. So saving the return value of getChar in an int, at least until you've checked to see if you've hit end of file or not. That's important. Sticking it in a char-sized variable and then trying to check it for EOF, that's going to cause you some trouble in some special cases. But it's easy to avoid that trouble just by storing this return value in an int-sized variable, at least until you've checked to see whether or not it's a legal character. So getChar is for getting characters 1 at a time from the terminal. PutChar goes the other way. If you call PutChar, it's expecting the numeric code for any character you want to print. You just pass that in as a parameter, just like getChar. It's expecting an int parameter, but if you want to pass in a legal value it can print, that's going to be an integer that's small enough to fit in a char-sized variable. So you just call this, you pass it the numeric code for whatever character you want to print, it prints it out, and it returns, it almost always returns the same value that you passed it. So what use is that? Well, it's useful in the special case when it fails. If you try to print a character and it can't, say, because the terminal has closed or because there's no more space to store, you've run out of room on the file system, then this will return EOF to show that it failed. Often, in every normal case, it'll return the same value that you pass it. Did someone start to ask something?
Dr. Jill, is that like when you do the input char int C, it will print a 67 or it will the letter C?
You can, I don't know what 67 is.
Is it ASCII value for the C, probably?
But if 67 is the ASCII code for the letter C, then you could pass in a 67 and it would print out the letter C. Okay. So it's expecting the numeric code. But what you're just talking about, how do you know the numeric code for each character? You almost never need to memorize that because of this next example. So this shows how you could use getChar and putChar in practice. And it kind of shows what I was about to say. A single quoted character means the numeric code for that character. That's how you normally put that in a program. So instead of remembering that 67 is the code for some particular character, you just put that character in single quotes, and that would evaluate to whatever number represents that character. And this little program tries to show that off. So in this program, we include the two headers we talked about. I've got one big main function. Inside the function, I'll point to it with my mouse here. I get the first character. And then as long as I haven't hit EOF, so as long as I'm still getting a character, I'm going to print out that character and then get the next character. So this loop is going to keep reading characters until there's nothing else. Printing out a character each time, but the character I print depends on a little bit of logic. I take the character I just read and I check to see if it's equal to a space. This is what I was talking about a moment ago. When I put that space inside single quotes, that's really whatever numeric code is used to represent a space. That's what it means. So I'm really comparing numbers here. It's just, I don't have to memorize what those numbers are. Here, if the code for whatever character you just got is a space, I don't print it out as a space, I print it out as a dash. Otherwise, I just print out the code for that character. So the effect is, this is going to keep reading characters from input. It's going to print them out to the terminal just like they came in, except it's going to replace all the spaces with dashes. Once I've read the whole thing, I return, and remember, for a C program, it has an exit status where 0 means success and any non-zero value means failure. Instead of using numbers for those return values, we've got constants like exit success and exit failure that are more readable. And when you include standard lib.h, you get definitions of those constants. So I'm doing what makes a lot more sense. I'm using numeric constants for this. These two functions are your main functions for character by character input and output for the terminal. Later this semester, we'll learn versions of these that'll work for any file you want. You'll use these on the text box program on your first project. Any questions before we try to move on?
Yeah, I had a quick question. So when you do get char, that function, so is it getting it from a different file? Is that what get char does?
It's reading from the terminal, so it's getting the next character that was typed by the user at the terminal.
Oh, okay.
The terminal inside your program, it behaves just like a file. So if you did IO redirection and you said, I don't want you to read from the terminal, I want you to read from this file instead, then getChar will really be tricked into reading characters from the file. But if you don't do anything like that, getChar gets the next character that was typed at the terminal.
Okay.
So the way this, I'll say this real fast. You normally the user types in a whole line of text. When they hit enter, the program starts getting the characters on that line. each time you call get char, you'll get the next character that you hadn't read yet, all the way up to the new line at the end, the \n that they typed.
Okay,
all right.
That makes sense. Thanks.
These two guys are for character by character IO. The next two we'll see are for, they're called formatted IO. They're for printing and reading bigger things than a single character at a time. That's what the F, question?
Oh yeah, go back to the previous slide. There was a question I had on there. That last line after the put char ch, the next get char that you were doing there.
Yeah.
What would happen if you omitted that one specifically and just college that?
Probably infinite loop. So if I forgot this line and I just did read at the start, if you typed in something at the terminal, you're going to read the first character, but you're just going to keep running around this loop, never reading anything else, but printing that first thing over and over and over again. If there was no input on the terminal, then you'd get EOF right away and it would bail out of the loop. But if they typed anything at all and hit enter, then you're going to get stuck in this loop, printing the same thing over and over again.
Gotcha. Thank you.
So probably not what you wanted, or probably not the behavior you would want. All right, so this is for formatted output. It's called printf, and that's what the F stands for formatted output. You probably saw a version of this in Java, because in Java, system.out has a printf function that is modeled after the one from C. In fact, lots of programming languages have behavior that works like C's printf. They borrowed a lot of ideas from that. In printf, printf always takes at least one parameter to the function, and that first parameter is called the format string. Inside the format string, you can put whatever text you want to print, and most of what you put in there will get printed out literally. So if you say the word value with a colon after it, when you run printf, value with a colon after it will be what gets printed out. But inside that format string, you can mix in what are called conversion specifiers. They're these things that start with percent, and they say to print something special mixed in to the output. Some people say interpolated in the output. A conversion specifier always looks like this. My next slide goes into this in more detail, but this one just says, I want you to print a floating point number using 6 spaces with 2 fractional digits of precision. So that'll print, and then I said printf always takes at least one parameter, a format string, but if you have conversion specifiers in your format string, then each conversion specifier says how to print one of the arguments that come afterward. So this one's here, this %6.2f says how to print this number 3.1415 in the output. There are a bunch of different things you can print with conversion specifiers. Here's sort of a way to read a typical conversion specifier. So inside the format string, they almost always start with the %. Or sorry, they do always start with the %. After that, you can have an optional field width. That number 6 says when you print this thing, always use at least 6 characters to print it out. This is handy for making columns line up nicely. You can say, well, even if this thing is smaller than 6 characters, pad it with spaces so it takes up at least 6 characters. So officially, this is a minimum field width. It says use at least this much. Here, use at least 6 characters to print this out. Pad with spaces if you have to. And then you can have an optional precision field. That's a dot followed by another number. The way precision works depends on what you're printing, but for floating point numbers, if you're printing out a real number like a float or a double, it says how many fractional digits to round it to. So here I'm saying round it to 2 fractional digits of precision. And then that last character of the format string says what you're actually printing. You have to, the last character of the conversion specifier says what you're actually printing. You have to wait till the end to find out, oh, you want to print a floating point number. That's what F stands for. That's for printing out a double value. And then this stuff says how to print it. I brought some examples for this. So let's say you were printing out the number, let's say you had a variable and you put 33.3 in it. And then you said to print that with a conversion specifier of %7.1f. So you're going to print it out as a double. You said to round it to one fractional digit, so you're going to get 33.3. But you said to use 7 characters to print it out, and you don't even need that much. So it's going to pad with 3 spaces on the left. And again, you could use this to make the columns line up nicely. This is something you'll use on your ballistics program on your first project. If we printed out the same thing using %14.10f, well, you ask for a lot more precision, so you're going to get a lot more zeros after the decimal point. You still don't have enough characters to use up 14 spaces, so here you'll get 1 space of padding on the left. In this last example, if you ask for a whole bunch of fractional digits of precision, you're going to see some floating point rounding behavior, because it turns out, even in a double, you can't store 33.3 exactly. It gets stored internally as the closest thing the computer has to 33.3. And in this case, you can kind of see that, well, we can't store it exactly, but we can store it as 33.299999 with some garbage at the end. That's the closest thing we can actually represent to 33.3. Since you asked for all those fractional digits, we actually need more than the 20 spaces you said to use. So it's going to store, it's not going to have to pad with any spaces in that case. Someone has their microphone unmuted, which is not a big deal, but you might want to check on that. Questions? All right, the only thing I've shown you so far is printing double values using %f. But there's a whole bunch of conversion specifiers, and many of them take the field width, and some of them use the precision that we talked about. %c is for printing a single character. So if you used a %c inside a format string, it would expect a numeric code of a character as one of the parameters after the format string. %d is for printing decimal integers. So it'd expect a number, an integer value after the format string. %ld is for long integers. C has a long type, but to print it, you need to use %ld. %f, that's the one we've been talking about. %s is for printing strings. We haven't learned how to store strings yet. We'll learn that a little bit later. We store them as arrays of characters, but once we know how to do that, %s is for printing them. And for sizes of things, we'll learn that C has a special type just for keeping up with how much memory it takes to store a thing. That type has its own conversion specifier, %zd, that we'll use mostly if we had to print out some debugging stuff. Questions about printf? We're going to use it all semester long. It'll be kind of like our what was it in Java, system.out.println. It'll kind of do that job, except it doesn't automatically put a new line at the end. Backing up a couple of slides, that's why in this example, after I print out this, that's all I wanted to print on a line, so I had to put the \n myself to put the new line character at the end of that line. Printf is for writing out formatted output. Its good friend scanf is for reading formatted input. It's got a lot in common with printf, and it uses a similar language for its format string. Scanf, the first parameter is called a format string, but instead of saying what to print out to the terminal, it says what to try to read from the terminal. Inside that format string, you can put conversion specifiers that say what you want to read, and they mostly use the same language we just talked about on the previous slide. I'll show you an example on the next slide. So the format string, the first parameter says what to try to read. Any parameters afterward, where I put this ... here, that says where to store what you're able to read, and we'll see in a moment how that works. And the return value, you can see it returns int. That says how many things it successfully read. So if you say read an int followed by a float, and it's able to successfully read both of those, it'll return a 2, saying I've successfully read both of the things you asked me to. If it just reads one of them successfully, it'll return a 1. And I've got some examples of that in a moment. So how would you use this? We said scanf expects a format string that says what to read, and that contains conversion specifiers for the particular things you want to read. So you might call scanf like this. scanf, remember %d says decimal integer, at least that's what it means for printf. It means the same thing for scanf. %d says read a decimal integer from the terminal, so typed by the user, and store it here. So you put in additional variables that say where you want to store the things that scanf read. But you can't actually do it like this first example. In C, variables or values are passed by value to a function, just like they are in Java. So when you call a method in Java, if you pass it a bunch of parameters, the method gets copies of those parameters' values. C works the same way. So if you called scanf and you gave it a format string saying, I want you to read a decimal integer, and you gave it a variable val where you want that stored, well, the problem is scanf can't actually change what's in this variable. It just gets a copy of what's in the variable, just like Java does. For this to work, you have to use the C mechanism for pass by reference. So in this top example, I'm trying to make the point that, well, scanf couldn't possibly work like this, because an integer variable like val gets passed by reference to, gets passed by value to scanf. It just gets a copy of what was in there. So it can't change what's in this variable. But if you put an ampersand in front of it, well, for now, we're going to say that's the C syntax for pass by reference. That's a way to give scanf this variable so that it doesn't just get a copy of what's in the variable, but it can change what's in the variable.
I have a question.
Sure.
So what you mean by this is that putting the ampersand is like you can give it in Java a primitive variable, and it's able to change that within like the entire program and not just within the single method.
Not entire program.
Well,
it's a way of, like if I had to compare this to Java, I would say it would be like having a way in Java to pass a variable so that the method doesn't just get a copy of what's in the variable, but it can really change it.
Mhm.
And in Java, there really isn't a mechanism for that, at least not for primitive types. In C, we do have a mechanism for that, and I'm telling you a half-truth right now. I'm saying, oh, this is a mechanism for pass by reference. Later, we'll figure out what it really is. But for now, we'll say this is what scanf needs to be able to change what's in that variable. So I got a bigger example here, and we'll talk about how it works. So let's say you wanted to use scanf and you wanted to read two things. You can put them both in your format string. So you can say, I want you to read a float, and I want you to read a decimal integer. Well, for that to work, you've got to pass a float variable by reference. So you have to say, here's where to put the float you're able to read. And then to read this decimal integer, you've got to pass an integer variable by reference. So I put ampersands in front of both of those. And now scanf will try to read a float and store it here. It'll try to read a decimal integer and store it here. How do you know if it succeeded or not? What if the user typed in garbage? That's what the return value of scanf is for. So normally if you're using scanf, you're going to want to look at what it returns, because that is the right way to know whether it's succeeded. So usually you'll save the return value in a variable, or you could put it as part of an if statement to see if your scanf worked or not. And I told you this already, but I'll remind you, it returns the number of conversion specifiers it matched. So if you say, read me a float followed by an integer, and it can't read either of those. Let's say the user just starts typing garbage. Well, it'll return a 0. I couldn't read either of those things. If it's able to read the float, but not the decimal integer, it'll return a 1. If it's able to read both of them, it'll return a 2. So it's returning the number of conversion specifiers that it successfully parsed. And it always starts from the first one. So it won't try to read this %d until it can successfully read the %f. There's a special case. If it tries to read something and there's no more input at all, it returns EOF. Remember, we've got that constant EOF, which really is just a name for -1. That's what it returns when there wasn't any more input. So this next sample piece of code shows how you might normally try to use scanf. You might, and it's kind of a silly example, but I prompt the user for an input. I call scanf and try to store it in this variable, but I save the return value of scanf, and then I can check that to see what happened. If the user typed in a legal integer, scanf should return 1. So I'll print out a message saying they printed out or they typed in a legal integer. If they type in garbage, scanf's going to return 0 because they can't match an integer. So I print out a message for that. If they don't type in anything at all, or if I hit end of file on standard input and we said, well, if they type control D, it should signal the end of file condition. In that case, I'll print out this message. There wasn't any input to read. Questions? We use scanf a lot this semester. It'll be it and kind of very similar functions will be our most common way of reading formatted input. I mentioned scanf uses a language that's almost the same as printf, at least for its conversion specifiers. And here's a summary, at least, of the stuff we'll need at first. And most of this is the same. %d is for reading in a decimal integer. So that's where the D comes from. Here's a place where it's a little bit different. In printf, %f would print a double. In scanf, you have 2 different values for printing, or 2 different conversion specifiers. %f will read a float. If you want to read a double, you need %lf. You can think of that as long float, which is kind of a weird way but that's where it comes from. So a floating point value that's bigger than a plain old float. So %lf is for reading doubles. If you wanted to read a long int, %ld will do that. If you want to read a single character, %c would do that. Of course, it'd probably be easier just to use getchar that we already learned about. But if you wanted, scanf can do it with %c. And if you wanted to parse a whole string, we haven't learned how to store that yet. But once we do %s, we'll read that. Where a string is, that means kind of like the .next on a scanner in Java. It will read the next sequence of non-space characters if you ask it to read %s. Almost all of these automatically skip white space. So if you say read %d and the user enters some extra white space, or they hit new line a couple of times, it'll automatically skip the white space looking for the next decimal integer. I said almost all of these automatically skips white space except this one right here. If you say to read a character with %c, you'll get whatever the next character is, even if it happens to be a space character. I brought a couple of examples to look at. So here, I've got a variable f value and I value. I go ahead and put initial values in those, but I'm going to overwrite them with this call to scanf. After I've declared them, I call scanf and I say read a float and a decimal integer and store them in these 2 variables and tell me how many things you successfully read. So let's say we call this, and then let's say the input is this first green box down here. So some spaces and then a 3 and then some spaces and a 4.12. What'll happen? Well, when you say to read this %f, it's going to look for the next thing that could be a legal float. This skips white space, so it'll skip all the spaces up to this 3. It'll see a 3 and then some spaces, and it'll say, well, that's a legal floating point value. So it'll store that in f value. So f value, this 1.0 that I put in there, will get overwritten with a 3. Then it'll try to read this %d, decimal integer. That also skips spaces. So it'll skip spaces up to this 4. It'll see the 4, which is a legal decimal integer, but the dot is not. So it'll stop right there on the reading. That 4 is a legal decimal integer. So it'll store the 4 in ival, and it'll leave this .12 unread. So if you try to read some stuff later, you'll pick up right at that dot. It successfully read a float and an integer value, so this will return 2. In this next case, well, I deliberately included some garbage. So if you call scanf and you try to read this 37.22b5, well, %f doesn't have any white space to skip. It'll read 37.22. That's a legal float, but this b isn't. So it'll store 37.22 in F value. It'll try to read a decimal integer. Well, but B isn't a legal decimal integer, so it'll stop right there. This B won't get read. The I value won't get changed. If scanf can't successfully read something, it doesn't modify your variable. So I val will still have a 2 in it. But how can you tell that it only successfully read one thing? That's what the return value is for. Scanf will return a 1 in the second case to say, well, I successfully read the float that you asked me to read, but I couldn't read the decimal integer. Questions about these?
Wait, so if you read like 3.14 and then it read 3 as a decimal first, will it read like 0.14 as the second float?
Here, I'm not sure I understand your question. For this, I'm only asking to read one float and then a decimal integer. So if you entered 3.14 and then a bunch of spaces.
Yeah, like if you reverse this, it should be %D. And
oh, D and then F. And the input was 3.14. Then the 3, I think you're right. The 3, so we're imagining this was %D and then %F. The 3 is a legal int, so it's going to get stored in the int variable. The 0.14 is a legal float, so it's going to get stored in the float variable.
Gotcha.
Yeah, I apologize. We're talking about an example that's not here on the slides. I wrote a bigger program that shows this off. So here, same thing, I include my 2 headers. Inside main, I'm going to try to read integers over and over as long as I'm successful. So I've got a place to store integers. I call scanf, telling it to read an integer and store it in that place. So I use the ampersand to pass that in. And since I asked it to read one thing, as long as it's returning a 1, it's successful. So I keep calling scanf as long as it successfully reads something. And then I print it out with printf, but I tell it to use a 6-character minimum field width. So it's going to pad with spaces to use up 6 characters, even if the number isn't that big. For this input, it's going to read 25 and print it out on a line by itself because I ended the line after that. So it's going to print out 25, padding with spaces. And then it's going to read the 12, printing that out, padding with spaces, the 77, printing that out, padded with spaces. But then when it hits this green, now that's not a legal integer. It's not going to skip past it and read the 62. So it'll stop right there. Scanf will return a 0 because it couldn't successfully read an integer. That'll bail me out of this while loop. So this is the only output I'll get in this case. Hopefully you feel pretty good about using printf and scanf. That's our quick introduction. We'll use these all semester long, and there's some more details that I need to fill in, but we'll save those until about day 8 or 9 this semester. Questions? All right, so let's talk about how C compilation works. And we'll start by comparing this to Java. I drew a picture down here at the bottom that shows how Java compilation and execution works. You know that Java has a compiler. You write down source files, usually ending with the .java. You run them through the Java compiler. And out of that, you get a .class file, at least for every class in your source. That class file consists of Java bytecode. So that's the output of the Java compiler, along with a lot of other metadata for defining the class file, for describing how that class works. But that class file isn't really ready to run on any real hardware. To run it, you've got to execute it inside a Java virtual machine. And as that Java virtual machine is running, it's probably loading a bunch of other class files that your program uses. Like if you use scanner, it has to go load the class file for that. If you read input, it has to go get the input maybe from the terminal. If you write out output, it's going to send that output to a file or a terminal based on what your program does. Every machine instruction inside your program, to run that on the JVM, it's got to run machine instructions on the CPU that do whatever that Java bytecode instruction says. Because of this, because every bytecode instruction kind of has to be emulated inside the JVM, Java machines or Java code can run a little bit slowly because the machine instructions that Java class files are made of don't really run on the processor. Pretty early in Java, they figured out some ways to improve this, and modern JVMs don't really emulate Java bytecode instructions. The first time they run each method, they do what's called just-in-time compilation. They take the code for that method and they compile it the rest of the way down to whatever machine instructions run natively on the CPU. They just do this the first time the method is executed, and then if you call the same method 100 times, you only have to do that once. Since that's compiled down to code for the native CPU, it's going to run a lot faster after you've done that just-in-time compilation. So this makes Java bytecode a lot faster than it would be, at least if we had to emulate the bytecode every time we ran a method. In C, they do this kind of thing from the start when they compile your program. So not during execution, but the C compiler compiles code all the way down to the instruction set that runs on whatever your processor is. Just like in Java, when you're compiling a C program, you take a source file. That's usually one that ends in a .c. We call that a compilation unit. That's the amount of code that the compiler sees all at once when it's compiling your program. That's usually one .c file along with all the headers that it includes. The C compiler writes out what's called an object file. That's usually a file ending in .o. That has the same, otherwise has the same name as the source file. The word object there doesn't really have anything to do with objects like you're familiar with in Java. That's just the name for a compiled C program. You can think of that as for every function in your source file, those are machine instructions to do what that function says. Well, just like a program that you write might use a bunch of other code, either code that you wrote or code that someone else wrote, C programs can be like that. So before you can run a program, you normally have to combine it with all the other code that that source file might use. That's the job of the linker. The linker goes out and gets, well, any other library code, like if you call printf, you didn't write the code for printf, the linker goes and gets the code for printf. If you made your program across multiple source files, well, normally you're going to compile them all separately. The job of the linker is to glue all that stuff together into one program that's ready to run. It's a bunch of, it's code for all the functions in that program that are already compiled to the native instruction set that's understood by your processor. Which means when it's time to run your program, you just have to load it into memory and start running at the first instruction in main. As your program is running, it could read input either from files or typed by the user. It's going to send output either to the terminal or to files, but it doesn't have to go in and load additional stuff as it's running. It doesn't have to do any additional compilation as it's running because it was already compiled to the native processor's instruction set. This, we kind of saw evidence of this on the first day. This is why the overhead of running a new C program can be a lot lower than it was for running a new Java program. There are advantages and disadvantages of these two models. We could say, well, the C model is a compiled model. When you take a program, you compile it all the way down to the machine instruction. Whereas in Java, even though you run it through something we call a compiler, there's still some additional steps that have to be done to make sense of Java bytecode during execution. So we could say to an extent, Java bytecode is interpreted. It takes a it requires a JVM to figure out what each class file says as it's being executed. There are advantages and disadvantages of each of these. Java, because it's not compiled all the way down to the native instruction set for a machine, it offers more portability and more platform independence. Whereas C, because it's compiled all the way down to the native instruction set for a particular processor, it's probably going to have higher performance. It can do more optimization because it can look at the whole program all at once rather than just one method at a time. But it's probably not going to have as good a support for debugging, because we don't know as much about the source code of the program we compiled. When we built that program, we just knew about the machine instructions that went into that program. that's all I got to say about Java versus C, at least for now. We'll return to that, and we'll see a lot throughout the semester. We'll see some consequences of some of what we're talking about here. Questions before we move on? I mentioned early in the lecture, I pointed to a preprocessor directive, and I said that thing #include, that's an example of a preprocessor directive. Now, the preprocessor is the first stage of compilation for a C programmer, or sorry, for a C program. You can think of it as kind of a dumb text-based substitution language for mangling your code before it gets compiled. Java doesn't have a step like this, but in C, it's an early step of compilation, and we can do some awfully neat tricks with that. And we've seen one example of those. #include for a header, that's a message to this preprocessor. It kind of says, go get what's in this header file before you look at the rest of the code. The next thing we're going to do with the preprocessor is we'll use it for defining simple macros. This will be our way of doing named constants, at least for now. And later we'll see some other things we can do with the preprocessor. But whenever you see a line of code in C that starts with a # and everything on that line all the way to the end of that line, that's really a message for this earliest stage of compilation for the preprocessor. Like I said, we've already seen including headers as one job done by the preprocessor. Defining macros, or for us, we'll call these preprocessor constants for now. A way of getting the preprocessor to give names for particular values. This will be a way of avoiding magic numbers in our code, using names for special values rather than just having to use the same value over and over again. The way we'll do this in C is for the preprocessor. If you say #define, and then you can give any name you want, and then a space, and then any value you want. You're telling the preprocessor, whenever you see this name, here it's size, I want you to replace it with a 25. So before the compiler even sees this code, or before the rest of the compilation sees this code, anywhere where size showed up is going to get replaced with 25. So we can use this to give any name we want, any value we want it to be replaced with. So like I said, this will be at least for now, our way of doing named constants, just simple textual substitution done by the preprocessor. If you have a definition like this for the preprocessor, then you can use size wherever you want. Like I'm showing down here in a for loop, if you wanted this for loop to run for some number of iterations. And then the preprocessor will automatically replace size with whatever you tell it to replace it with 25 before the compiler even sees it. This for now #define can do a lot more than just replace one word with one value. But for now, that's what we'll use it for. We'll use it as a way of having names for special constant values. I talked about how the preprocessor is the first stage of compilation. Well, how many stages are there? What happens in each stage? I got a slide for that. I've listed what normally happens when you compile a C program. And it takes a few slides to cover this, but here at the start, you write your source file. And in it, you can include regular lines of code and messages to the preprocessor, like this #define. And we already said the first thing that happens is your code goes through the preprocessor, and you get what's called expanded source code. The preprocessor, among other things, it replaces definitions with their values. So some people will say it expands those definitions. So that's why the result of preprocessing is called expanded source code. And then the earliest stage of compiling your program is looking for the tokens. This is sometimes called tokenization or lexical analysis, sometimes just called scanning the source code. Like I've tried to show in my picture, that's kind of looking for the words and symbols in your program, the variable names, the operators, the punctuation in your programs. That's what lexical analysis does. Once you have the tokens, parsing figures out the structure of your program. Usually creating something called a parse tree. If you think of this statement here, length plus equals base times 5, you can think of that as an assignment operation where I'm taking some expression and using it to update this value. Now, the structure of that statement, I've tried to illustrate in this little tree here. A parse tree has it's a tree-shaped structure that reflects the organization of the expressions and statements in your program. Once the parser has figured out the structure of your program, we can start generating instructions to do what that program says. From the parse tree, we can do code generation, and I've tried to illustrate here, the output of code generation is usually human readable instructions for how to do what that parse tree says. In fact, I tried to make up plausible instructions that would do what this assignment statement says. In the next class you'll take, assembly language class, you'll learn how to write and make sense of code like this yourself. That's usually the output of code generation. It's human readable, so it requires one more step to get it into instructions that can run on your processor. That's what the assembler does. It turns human readable assembly code into object code. And we already talked about this, into a file that contains the machine instructions to do what each of your functions says to do. This is usually not human readable. I wrote out a string of bits here to show this is usually a sequence of binary values that's meaningful to the processor, but not easily read by a human. Object code contains the machine instructions for each function. We already said to get a program that's ready to run, we have to glue together all the machine instructions for every function our program needs, so that if one function calls another, it has the code to execute that other function. And that's the job of the linker. The linker takes object code from code that you wrote from library functions and packs it all together into an executable containing machine instructions for everything our program needs. We spent a little bit of time talking about what the preprocessor does and what we're going to do with it, at least for now. We said, well, the next step in compilation is lexical analysis. It's looking for tokens in our program. And I've said informally, well, the tokens are kind of like the words and the operators in your program. I guess more specifically, I would say, well, a token could be an identifier, a variable or function name that you made up. It could be a keyword in the language, like void or while or for, or reserved words like int. Could be a literal value like a number or a string like that next example. Could be an operator in the language like times or plus plus or assignment. It could be a separator or punctuation like curly brackets or semicolon. The lexical analyzer looks through the sequence of characters in your program, and it looks for tokens of these types. Usually it uses things like regular expressions but internally, to kind of quickly find the tokens in your program so that we can figure out the structure, so the compiler can figure out the structure of your program. Well, to do this job, it has to be able to find backing up a slide. The first one I said were identifiers, names that you pick. What are the rules for identifiers in C? I think they're the same as they are in Java. An identifier can be any sequence of letters, digits, and underscores, but it can't start with a digit. So if you're picking a name for a variable, a name like size would be a fine variable name. A name like x2 would be a variable name, or even x_2. Any sequence of letters, digits, or underscores, it just can't start with a digit. So a input like 2x wouldn't be a legal identifier name. In fact, the lexical analyzer would say, oh, that's the number 2 followed by the variable x. So identifiers can contain digits, they just can't start with them. Just like in Java, the scanner in C, the lexical analyzer, is case sensitive. So a variable name like my value is different from my value with a lowercase v. We said the scanner has to recognize identifiers. So these are the rules it uses to find identifiers. It has to recognize reserved words. And well, there's a fairly modest collection of reserved words. Most of them are the same as the reserved words in Java. I listed all the reserved words in the oldest standard for C, the 89 standard. The C99 standard added a few additional reserved words like inline and restrict. Learning this list is pretty easy because all the ones in black are the same as in Java. So break, case, char, default, do, those are all reserved words in both languages. Only these red ones are unique to C. So auto and extern and register, you might want to pay attention to those because you didn't have those in Java, but they are reserved words in C. I mentioned, or I colored two special ones in purple here, const and goto. Those are reserved words in Java. They just don't actually do anything in Java. They marked them as reserved words in the language, but either out of spite or they never got around to it. They never actually used them for anything in Java. You still can't name a variable const in Java. It's just, it doesn't do anything in Java. You can't use it as, you don't get anything useful out of it. So here, the tokenizer has to recognize these special words as reserved words. So I made up some work for the tokenizer. Let's say, first let's make it easy for the tokenizer. If you had to input like A space plus B space greater than or equal C minus minus space minus D. Well, the tokenizer's job is pretty easy there because I put spaces between a lot of the tokens and none of the tokens have spaces in them. So plus has to be a token, A has to be a token. Well, here plus plus is an operator followed by a variable name B. So here finding the tokens is easy, but how about if I gave input like this? A plus 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 B greater than or equal to C, the tokenizer could still make sense of this. But you and I need to be able to figure out what the tokenizer would do in this case. Well, is this an example of A and then plus plus followed by plus B? Or is it plus followed by plus plus B like it is in this top example? Or is it 3 single pluses in a row? Well, there's a simple rule that describes what the tokenizer is going to do in this case. And it's not really about precedence because until we know what the operators are and until we know what the tokens are, we can't tell what their precedence should be. So the tokenizer has to figure this out just by looking at a sequence of characters. Fortunately, it's easy. The rule of the tokenizer is it always tries to get as big of a token as it can. Think of it as being greedy. You'll sometimes hear this called a max munch algorithm. It tries to make the biggest token it can before moving on. So if you take this example, like backing up A plus 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 B greater than or equal to C minus 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 D, well, it's going to see the A and say that's a legal identifier, but A plus isn't a token at all. So it's going to stop after the A and say that's the first token. Then it's going to try and find the next token. Well, plus is a legal operator, but so is plus plus. But plus 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 is not. So it's going to say plus plus is the next legal token. And then plus is a legal token, but plus B isn't a legal token by itself. So plus must be the next token. Continuing, B must be the next token because B greater than doesn't mean anything. Greater than or equal is a legal token. And that's the longest one we can make because greater than equals C isn't a legal token. And if you continue, you'll see this happening throughout this example. The tokenizer is always trying to, you think of it as continuously adding characters until the next character couldn't be part of a legal token. I made up an example where you could try this. I'll let you think about it for just a moment yourself. Just try to find the tokens. So hopefully you made it through part of that. Let's talk through it together, at least for the first part of it. I don't think this would compile to anything legal, but the scanner can still find the tokens And then it's the parser's job to decide whether or not this is part of a legal program. And the scanner could make sense of this. First token is going to be minus minus because that's a legal like poster predecrement. And then another minus minus. And then XY is a legal identifier name, but XY plus doesn't mean anything. So XY is the next legal token. Plus is a legal token, but plus minus isn't. So plus is the next operator. Minus equals is the next operator. X is the next legal identifier. Plus plus is a legal operator, so that's the next token. And we won't continue there, but you can use this thinking to get through the rest of these examples. And this is usually a good, easy exam question, is to give you a string that I made up like this and let you find the tokens in it. So the tokenizer can scan and make sense of arbitrarily ugly looking input like this, including this example. In fact, C lets you write such potentially cryptic code that they've had a contest for writing deliberately obfuscated C code called the Obfuscated C Program or C Code Contest. I don't know if they're still having this. I haven't checked on it lately, but this is an early winner of this contest. This was a legal C program that prints out hello world. It's just not super obvious that that's what it does. Here's a later honorable mention that's actually written by a friend of mine years ago that my understanding is this evaluates expressions in octal written out in base 8 instead of base 10. You can see they made it hard to understand, at least the author did, by packing all the symbols together, making them spell out the Roman numeral 8. But otherwise leaving out a bunch of spaces. This shows what you can do with help from the C tokenizer. You don't have to make it easy for it to read, but you probably wouldn't want to do this. I wouldn't want to have to debug a program that's written this way. So even though we could write our code so that it's hard to read, we don't usually choose to do that. Which is one reason we have coding style conventions in this class. We follow additional rules. Any workplace would probably have some degree of style conventions that say, even though we could write our code crazy ways like this, we choose not to do that. We're going to try to make it easy for people to read and make sense of our code by following at least some rules together. And in this class, we have rules like that. I didn't make them up. I inherited them from the person who taught this class before me. I've made some small changes to them. I don't necessarily agree with all of them, but that's not the point. Often you'll be expected to follow coding style rules. I think you may not agree with all of them, but you agree to cooperate with your coworkers. So we're kind of simulating that here. I mentioned up at the top of our Moodle page, we've got a document that describes our coding style rules. And I thought I would go through them real fast in class. You'll want to read that document so that you don't miss any of them. But at least on the projects, we'll be paying attention to the style of your code, not just whether it works and not just how you designed it. So among other things, our coding style rules say that you'll have block comments, Javadoc style block comments, at the top of every source file and in front of every method, or sorry, every function in C. At the top of every file, in addition to saying what that file is, you'll have a tag for the file name. That's necessary for the utility that we can use for extracting the Javadoc comments out of a C program. So you have to help it out by saying what source file it's parsing. And you're expected to have an author tag. So say who you are, including your name and Unity ID. In front of every function that you write, you'll have a Javadoc comment that summarizes what the functions are, what the function does, along with its parameters and its return value. If it's a void function, you don't have to have a return tag. So if it doesn't return anything, that's fine. If it doesn't take any parameters, you don't have to have any param tags. But if it does take parameters, we're expecting a short description for each of them. Style-wise, if you like to put stars at the front of every line, that's fine. If you don't want to put stars at the front of every line, that's fine too. It needs to start with /**, just like every JavaDoc style comment. But whether or not you duplicate that star or exactly how you line this up is up to you. And probably your editor has in mind some things it wants to enforce about that. So we try to be flexible on that. I'm trying to think if there's other common questions about this. So these are what we expect in terms of block comments. We're also in your code, we're expecting you, just like you've probably done in previous classes, we're expecting you to avoid what some people would call magic numbers. These are places in your code where you've got numeric constants that don't have an explanation. This would be, instead of expecting particular numbers or instead of looking for particular values as magic numbers, we kind of try to look for reasons why it might be good to have a name for a constant. So I've given 3 examples that we typically look for. Like if you've got a value that has an explanation, but you just wrote out that value, like this is obviously supposed to be pi. Instead of just duplicating the number pi everywhere, it would make more sense to use a named value for that. That would help with readability. So in that case, we would call this a magic number. You should use a preprocessor named constant for that, like we talked about making earlier in class today. Anything that's potentially a tunable parameter, like if you're writing a video game and you get a score for a particular thing, well, it'd be easier to make that consistent and tunable by having a named value for that rather than just putting that number right in your code. Or if you've got places where the same number has to show up exactly the same in multiple places, it would be good to have a named constant for that. Otherwise, we would call that a magic number. So this is what we look for when we're grading your projects. Not on the exercises, we don't enforce the style restrictions on the exercises, but we do on the projects. So we take time to look through your code for things like this. The style guideline also has some restrictions on things like curly bracket placement in general. Curly brackets go on the line, of code that introduces the curly bracket. So if you have a for loop, the curly bracket goes at the end of the for. If you have a while loop, it goes on the same line as the while. The only difference is for function definitions. For function definitions, the curly bracket goes on the next line after the function header. And I would say that's to call attention to function definitions, to give them a little more vertical space so they stand out. And that's a fairly common convention, even when curly brackets go on the same line for everything else. For indentation, we're using spaces instead of hard tabs. So inside, you're expected to indent your code. Inside a for loop, inside a function definition, the code should be indented. You can indent it with as many spaces as you want. You just need to be consistent. So if you want to indent with 2 spaces inside a for loop, that's fine. Just don't use tab characters. You can probably get some help from your editor on this. I know for the editor I use, I don't actually have to hit the space character a whole bunch of times. It automatically indents by the right amount for me, and I can tell it to indent with spaces instead of using hard tabs. So I encourage you to think about how to get your editor to help you out with this. I think there's one more style guideline we'll talk about, and that is avoiding global variables. You don't really know how to do global variables yet, but I'll say in C, well, you can have functions that aren't part of any class. You can have variable definitions that aren't part of any function. They're called global variables, like this little fragment of code I gave here. This variable cost is defined outside a function. It can be accessed from any part of your program. This lets you do some awfully neat things, but it also can create a lot of problems, especially if multiple developers are trying to work together. For that reason, it's good to avoid global variables, and that'll be our rule. On projects, you shouldn't use global variables unless we ask you to. Early on, there may be some cases where we say, just use a global variable for this. But for realistic projects, global variables should be avoided, and on your projects, unless we tell you to use one, you'll want to figure out how to code around needing global variables. That gets us to the end of our lecture material for today. I'll go ahead and stop the recording in just a moment unless someone has a question.
Dr. Chell, I have a question. Earlier, what's called the comment style.
Yes.
Java style. You say that like, do we need to write the summary description of the the function first and then program tag second, right? You understand what I mean? Do we need to write like a summary, the explanation of the a function first and then tag?
Yes. Yeah. So I think you're talking about this. If you're putting a block comment on a function, you put the summary of the function first, and then any additional tags, usually on a line, each of them on their own line after that. And one more thing I'll say, I meant to mention this earlier. Later, we'll learn how to define a function in one file and mention it in another file using something called a prototype. When we learn to do that, and I'll remind you of this when we talk about it, when we learn how to do that, we'll start commenting functions in a header file if we prototype them in a header file. So normally the comment goes before the definition of the function, unless the function is prototyped in a header file. We haven't learned how to do that yet, but that'll be something to remember in a few weeks. I'll go ahead and stop recording, but as always, I'll hang around after class for people who want to ask questions, and we can stay and answer questions. Let me just stop the recording.
All right. One other question. In what conditions?
Let me stop the recording.